Okay, so what we're going to do here is we're going to pick up where we left off from last section. We left off, and if you recall from last time, the main theme of last class was we were describing the different types of electrical waveforms, right? We said that electricity can move through a circuit in either the direct current form or the alternating current form, right? And we described how you could, in principle, use a spinning magnet near a conductor, a conducting wire, to induce alternating current, to make electricity shake back and forth in the wire, right? To make an electric current, an alternating electric current. So last class we left with not this picture, but we left with a idea like this, where we could, in principle, spin a magnet and induce current in a nearby conducting wire. That's the last thing we talked about. Okay, so hopefully you remember the sine wave, that positive and negative alternating wave that we use to describe electric current, and we're going to basically pick up from that, move on, and add more to it today. So there's two ways you can use that idea. You can either use that idea to generate electric current by putting mechanical work into a rod that would, for example, spin a magnet. Okay, we call those generators. So you see on the left, they have a crank attached to a rod that spins. In this case, an actual magnet, right, would spin wrapped inside of a wrapped coil of wire, and in principle and practice, that can induce current in that wire. Okay, so by spinning that little handle, okay, you can make electricity move through the wire. That's exactly how your car's alternators work. Okay, you guys know your cars have a battery, right? The battery runs things in your car, for example, when your car is off, okay? And like if you go to like a drive-in movie theater or something, you sit with your car off for a while, or your car on for a while, but it's the engine's turned off, but your electric stuff's all on, radio's on, right? And you can play that all, but eventually, like, your car will, the battery will begin to die, right? So what do? You turn your car back on, right? Charge your battery for a little while, okay? What's happening when you turn your car back on, and to charge your battery, your engine spins, right? Your engine rotates. There's a belt somewhere on this attached to your engine, the spinning part of your engine. That belt will go to an alternator. That alternator is spun with the energy from your engine. Okay, so instead of having a hand on a crank, okay, your alternator uses the power from your engine to spin, and it's actually not a little magnet, but in this case we'll say it like that, to spin a little magnet, okay, and induce current, and that current running through here, when your car spins this little rod, will send electricity back to your battery, charging your battery, putting the potential back in your battery, okay, charging the battery, okay. We call that a generator. In fact, when the first automobiles were produced that had batteries and had to have a way to charge them, they actually referred to those devices as generators, not alternators. We call them alternators now because they use alternating current, and they still did back then. Just the terminology has changed a little bit. So if you go buy an old 1950s car and you need to replace that part of the motor, you'd go ask the AutoZone people for a generator for that car. Okay. As well, if you have like an RV or something like that, or a little travel trailer, and you want to have power when you're out in the boonies, right? You can take a car battery with you, right? Plug into the car battery, but then as soon as your car battery dies, all of your lights in the trailer go off, right? So what do? You bring a generator with you, okay? Gas-powered generators use a gas motor to spin, and in this case is a little magnet, to charge a battery. Okay, generators do that. That's why you can buy a gas-powered generator, use gasoline to charge a battery. So that's what it's doing. So and I'll give you the definition in a moment. So that's a generator. On the right, the exact opposite principle can be used. Okay, instead of using the magnet and using mechanical work to induce electricity through that coil of wire, you can run electric current through the coil of wire to spin the magnet. Okay, the exact opposite, right? If that magnet spins and is attached to a axle, and the axle is attached to a wheel or a fan motor or something like that, then you can use it to spin a wheel, spin a fan motor, and we spin a fan, and we call those motors. So there's two things that operate on this principle of induced current. Okay, notice the magnet doesn't touch the wire. Okay, so the wire and the magnet are both separate. It's current being induced in the wire by the spinning magnet, or the magnet being spun by current in the wire. Either or, okay? If you are spinning the magnet and inducing current in the wire, you have a generator. If you're running current through the wire and then using that current, the electric current, to spin the magnet, then you've created a motor. Okay, some can go back and forth. Good. So this is what we'll call generators and motors operating on the principle of induced current. Here's our definitions here. Generators take mechanical energy, the energy of movement, and convert it into electrical energy. What do you guys know about energy? Tell me something about energy. So those of you who've been with me for a while should know what I mean when I say tell me something about energy. One more time?
Energy is never lost.
Right. So energy's not lost, right? But it can be converted into other forms. Okay? Forms of energy are, for example, electrical energy, okay, and mechanical energy. And using this principle of conservation of energy, this is one of the laws of physics that we really, really like, okay? It's called conservation of energy. There's a bunch of these conserved quantities in physics, which we'll get to, but one of them is conservation of energy, okay? So energy into a system, like a motor, has to equal the energy coming out of the system, okay? So whatever energy you put in, you get out. Now that energy might not, so for example, go back to here. If you put some energy, some work into spinning that crank to spin that magnet, all of the energy that you put into spinning that crank is converted into other forms of energy. But importantly, it is not all converted into the electric current. Okay? So, you know that when electricity runs through wires, those wires heat up, right? That's energy escaping the wire. It's leaving its heat. Heat didn't come from nowhere, right? So it is true that all of the energy that you put into a system is conserved. It comes out the other side. But it doesn't all come out in one form, okay? I can use mechanical energy to create electric current, converting mechanical to electric, but it's not all converted into electric current. In fact, most of the energy that you are using to turn that generator is being turned into waste energy, waste heat mostly, okay? But it is true that all of the energy is conserved in some sense, okay? So if you could track down every little heat wave, every little sound, every little vibration, every little movement of electron, it all is accounted for. Everything you put in, you get out. It's just not all taken out in one form. But it's true that energy changes forms and is conserved. Okay, so back to this. So generators take mechanical energy, movement, and convert it to electrical energy. Motors do the exact opposite. They take electrical energy and convert it into mechanical energy. What's really interesting are electric cars. All electric cars use some type of battery to spin some type of AC motor to spin some tires, to turn the tires, okay? But some electric cars have what's called regenerative braking, okay? You guys know that you have brakes on your cars, right? And what they roughly speaking are is attached to the rotating wheel, right, is a metal disc, right? And when you want to stop your car, two brake pads clamp down on that metal disc, okay? Those brake pads create friction on the disc, creating heat and noise, right? That heat and noise is the converted kinetic energy of your car. Your car slows down, right, when you put your brakes on. So what happens is your car has some energy because it's moving and it has mass. You clamp your brakes onto your car, and the energy of you moving fast turns into heat and sound in your brakes. You're converting energy, okay? And where does that heat and sound go? Just out into the world around you. It's not captured, okay? In principle, that energy could be captured, okay? So what you have in some electric cars is the AC motor that's used to spin the wheels when you want to put the brakes on the car. So when you apply the brakes on these electric cars, if they have regenerative braking, they can, as you're trying to brake, not use the brake pads to just create waste heat and slow the car down that way, but will actually use the AC motor run in reverse. Okay, so as you, basically power stops going to the wheels, right? And the wheels continue to turn because the weight of the car is pushing the car along, right? And the power will be fed back through the motor because the wheels are now turning the motor, okay? And power goes back to the battery. So when you brake on these regenerative braking electric cars, you are putting power back in the motor. What would have been waste heat, just wasted out into the environment, is now put back into your battery, excuse me. Put back into the battery, and then you can use that to propel you down the road. Again, it's not perfect. You don't put back everything that you have used, right? But some of the power that you use to propel the car down the road and bring it up to speed is then put back into the battery as you brake, as you apply the brakes on these vehicles. Really, really smart stuff, right? It's taking a motor, and then using it as a generator when you're stopping. Okay, so when you're going, it's a motor, and when you're stopping, it becomes a generator. Really nice little tool. And the idea is simple because a motor is just a generator run backwards. Okay, not literally spun backwards, but the power coming from the wheels and going back through the conducting wires. All right, so you're going to have two parts to each any AC motor. There's always a rotor that spins, something that rotates and is attached to either wheels or something else, a fan blade, some pulleys that raise your window up and down, right? Or move your windshield wipers back and forth. Something's got to spin. That's the mechanical energy part of it. Okay, remember, all motors take electric energy and convert it to mechanical. So something's got to move. And then there is a stator, which is wrapped around the rotor. So not touching the rotor, but somewhere around the rotor is a coil, a series of coils of wire that electricity will run through. Okay, surrounding the rotor, electric current passed through the wires, causing the rotor to spin. Now what's really neat is, the way we've been describing this is, you have a magnet attached to a rotor, and the magnet is either being used to induce current in the wire, or the wire it has current running through it, and is then acting and forcing the magnet to spin around. So you either have a generator or a motor, but the whole time we've been talking about the rotor part of it, the thing that spins, having a literal bar magnet attached to it, right? Here's the neat thing. Because of these laws of induction, current being induced in nearby wires, you actually don't need a magnet. Okay? So the next thing to learn is, in induction motors, there is no magnet. Okay? Both the stator wrapped around the rotor and the rotor itself consist of just coils of wire. Induction motors are motors that use only coils of wire for both the stator and the rotor. The principle that's being exploited here is called electromagnetic induction. I'll try to explain better on this upcoming slide, but hopefully you have had enough exposure to this by this point where it's starting to make sense. You can credit Nikola Tesla for the creation of the AC motors, which is why the company called Tesla is called Tesla, because that's what they do. They make electric cars, and electric cars use AC motors. Okay. So to show you, give you an idea of how this works, right? So this all refers back to chapter 6, which talked about magnetism and electrostatics. We talked about the ability to induce current in a nearby wire. So here's the idea. looking just at the top wire, these are two wires, looking just at the top wire right now, if you run electricity through a wire, electric current moving in a direction, okay? What we learned is any moving electric current generates a magnetic field. You guys all know what magnets are, okay? So the magnetic field is just the field around the magnet that would act on like iron filings or something like that, okay? Any moving electric charge generates a magnetic field. Magnetic fields bloom perpendicular. They bloom away from the charge. So the direction of charge runs this way through a wire, let's say from left to right. Then the magnetic field coming away from the wire moves up and down. Okay, it spreads away from the wire. And remember, this is alternating current we're talking about. So the electricity goes that way, then back that way, then back that way. Okay, 60 times per second. Okay, 60 hertz alternating current. Right now we're not showing it shaking back and forth because we're just trying to give you the simple explanation of how current can be induced in a nearby wire. So this would, for example, be if we have a motor, okay, this would be the stator. So this coil of wire would be wrapped around the outside of a rotor. Okay, so suppose a coil of wire wrapped around the outside of a rotor, and you run current through it, the magnetic field blooms. You know that magnetic fields, well maybe you know, but we've learned this. We know that magnetic fields can induce electric current in a nearby wire. We just said that earlier that if you take a magnet and move it near a wire, it makes the electric current move. It makes electricity, okay? So the whole idea of spinning that magnet was taking a magnetic field and using it to make electric current. Now we're taking electric current, using electric current to produce a magnetic field. Okay, the electric current produces a magnetic field in the wire that it's running through. That magnetic field induces current, creates current in this wire, the lower wire, without having touched it. Okay, the magnetic field touches the wire. So the magnetic field shifting back and forth in this upper wire because the electricity is moving back and forth. This magnetic field, blooming that way, if this wire is close enough, begins to drag the electrons in this wire back and forth, okay, causing electricity to move in this wire. This wire gets its own magnetic field, okay, and now we've got mutual induction, okay. They're both inducing current in the other, one inducing current in the other. Here's what's interesting. There's a law called Lenz's law. L-E-N-Z, Lenz's law, which says that whatever direction the current is running in the inducing wire, in the primary wire, the induced wire sends current in the opposite direction. It's not that important for practical purposes because we don't care, but it's neat to know, it's interesting to know that the current actually runs the opposite direction. Okay, so electricity goes through this wire, causes the electricity to move through this wire. The only thing they're not showing you here is that these are circles. These are coils of wire, not straight lines. Okay? So we're about to make them circles in a second. Okay, good. So that's great. That gives us everything we would need in principle to make AC motors, to make something that would spin a wheel. Okay? And what do we spin wheels with? And what do we spin in the X-ray machine? Well, we're going to talk about the tube, X-ray tube today. Inside the X-ray tube, there's a disc like that, okay, called the anode, the positive side of the X-ray tube. This thing has to spin at about 3,400 RPM. Has to spin really fast, okay? And what you're not seeing, because I've taken the glass all off of this, is, and if you read the book, you saw this. This whole thing is encased in a glass tube, a glass envelope around this with some other components on the other side. The stator that runs electricity through it to spin this is on the other side of the glass, okay, not touching, not inside of here, okay? So we need a way to make this thing spin, right, while it's encased in glass and nothing actually touching it, okay? So in order to do that, we need an AC motor. This thing is what is spun by the AC motor, okay? So this is the stator side of the AC motor. Okay, the stator's gone now, and so is the whole rest of the X-ray tube. Okay, so that's good. We want to have mutual induction, so that we can do things like spin this disc, and later on we'll learn why it's important to spin that disc, but inside our equipment it's important, and in all of your car, we use it in our cars every day to have these, to move things. These little AC motors move all kinds of things in your cars. So the next thing we'll want to know is how can we use the principle of induced current to change the power, right? To adjust the power we're getting when we plug into the wall, okay? We know that X-rays require a lot of power to generate. We need something called a generator to make the X-rays happen. And so we need to learn how we get, coming from 110 or 220 volts from the wall, how we convert that into, 100,000 volts, right? Or more, okay? So the next device we're going to learn about is called the transformer. So transformers are part of the X-ray generator. Okay, we're not directly talking about generators right now, but we'll talk about transformers real briefly. Okay, so in a little bit here we'll look at the circuitry, and you'll be able to identify where the transformer is in the circuit. But let's go ahead and work through this. And in fact, yeah, that picture's okay. Well, let's do that. Let's just say it like this, because I got better pictures in an upcoming couple of slides. Anyways, an accidental discovery in the early days of learning about electricity. Transformers are really neat devices that can alter the voltage and the amperage of electrical current. What law have we learned that tells us about how voltage, amperage, and resistance play together? Not Lenz's law. Lenz's law says that current running this way will send current the other way. Ohm's law, right, says that voltage in a circuit is equal to amperage times resistance, right? You remember, hopefully, Ohm's law. As being voltage is equal to amperage times resistance, okay? Transformers use Ohm's law and mutual induction. So here's the idea. If you take, I keep my laser pointer to point at it. Over here in this picture, let's just zoom in on this picture. If you take a coil of wire, right? Take a wire and take a circular magnet, or in this case it's shown as kind of a square magnet. The square magnet will lock down the magnetic field lines. It will keep the magnetic field lines within the magnet itself. Okay, so you know that like horseshoe magnets, right? Take the magnetic field and focus it. Maybe you haven't seen horseshoe magnets. Horseshoe magnets are shaped like a horseshoe, right? So a normal magnet, like a bar magnet, right, would have a positive, using electricity terms, a north and a south pole, right? And the magnetic field lines for a bar magnet would move, for example, out of the north pole into the south pole, like that, right? So if you drop a bar magnet down and then you drop a bunch of iron filings down, the iron filings will all line up like that, right? A horseshoe magnet's a little different. A horseshoe magnet is a bar magnet, but bent in the shape of a horseshoe, okay? So this is the north pole, this is the south pole. The field lines now extend out of the north pole to the south pole. So they're concentrated, okay? You can see that that's spread out, magnetic field lines are spread out. They're now concentrated here, okay? So what if instead you could just, that's not even a good drawing. If you could just, as they show here, right, have the north and south poles basically be just connected, okay? So you take that out, and any induced magnetic field will be stuck within the magnet itself. So you can see from this to this to this how we can focus and concentrate a magnetic field, okay? Very spread out, more concentrated, and now the north and south pole are touching each other, so it's very concentrated. There is no, it's still a dipole, it still has a north and a south pole, but it's all sort of contained now, okay? So what you can do is, you can wrap, comes in this way, you can take a wire, wrap it around, wrapping around, right now it doesn't matter how many times it's wrapped around, but you can take a wire, run it in, wrap it around one side of this square magnet, okay, this closed magnet. and now you're sending current in through one end and out the other end, and nothing changes. These two ends are equal to each other, right? What goes in comes out, okay, minus some waste heat and stuff, okay? However, if you choose to run a wire along the other side, okay, like that, if the wire running along this side has the same number of coils as this side, you can send current in through here. The magnetic field moves, inducing current in that wire without touching it. Okay, so this wire creates current in that wire without it being touched. So and current would run like that. Okay, without touching. This is mutual induction, like the AC motor, but with nothing spinning. Okay. So that's what transformers do. Now, if we wanted everything to just be the same, okay, we wanted the power on this side to equal the power on that side, we would have, 10 windings over here and 10 windings over here, okay? And everything would just be the same. Power in would equal power out, okay? What do you guys know about the length of wire and resistance?
More wire, more resistance.
More wire, more resistance, right? So, let's go over to here. If this number is fixed, if you can't change that number, the amperage number is fixed, okay? And if the resistance number increases, okay, what has to happen to the voltage? If they're on opposite sides of the equation, opposite sides of the equal sign, they have a direct and proportional relationship, okay? If this number doubles, that number also doubles, okay? Just basic math would tell you that this number has to double if that one doubles. The relationship is opposite sides of the equal sign are direct and proportional with each other, okay? So if you say, I'm going to fix the amperage, I'm going to run a fixed amount of amperage through this, but on this side, I'm going to add more coils, okay? I'm going to add more coils equals more, longer wire equals more resistance, right? So I'm going to put, 100 coils on this side and 200 coils on this side, 200 wrappings on this side. This side would have twice the resistance, okay? So the voltage would have to be twice as high on this side, okay? These would both have the same total power, okay? But one side would have one voltage and the other side would have a different voltage number, okay? We would call that a step-up transformer, okay? If instead this side had, let's do it like this. If this side had 100 coils, okay, 100 windings, 100 wrappings, and this side only had 50, okay, the secondary side, this side, would have less resistance, okay? Now the relationship is if resistance were to go down, voltage would go down. So this side would have some voltage, some amperage, some resistance. This side would have less resistance, so less voltage. It would be a step down transformer. Yeah.
Is that why some chargers, phone chargers, are slower? I have like 2 boxes, right? I have a 5 volt and I have a 10 volt. 10 volt's going to charge faster. But there's also 2 different kinds of cables. So the faster charging cable just means that the cable is probably thicker, so it could run more current.
Yeah, so it would have thicker means less resistance, right? If this number, so they're fixed voltage in those. So the voltage would be fixed. V-I-R. Voltage would now be fixed, right? With a thicker wire, resistance goes down, so this number has to go up. Amperage would go up. Amperage is current, more current, faster charge. Yeah. So when you look at phone chargers, look at the total wattage that they provide, the power, right? Volts times amps, right? And that'll tell you more about how fast it's going to charge. But yeah, you can look at each individually now.
I tried on my 10, 15 volt little charger. My girlfriend gave me cable that she had, but the cable was just trash. I have
Yeah.
seen the same thing. It happens a lot more frequently with the Type C chargers.
Yeah.
So I have a lot of them. That
So
are
that's why, like, when you go buy a phone charger, right? You're just like your charger cable. You can buy like $5 charger cables at the gas station that are gonna work for a minute and break, right? Or you can go buy the whatever $20 or more Apple ones or whatever, whatever you've got, nicer ones. Pay more for them. One, they last longer because it's a higher quality material, and the higher quality material also conducts electricity better. Okay, so you get faster charging and a longer life out of them. So it's sometimes worthwhile. If you have to buy 4 $5 chargers in a year, you're spending $20 on charger cables a year. But if you buy one $20 charger that year, then you're only spending the same. You're spending the same amount of money, but going to the store less, right? To buy replacement cables. So cheaper is not always better, right? Might save us money in the short term, but not the long run. So yeah, those are all definitely things to think about, and so you can see how this stuff applies to like everyday life too, right? Anyways, the purpose of having a transformer in the X-ray machine, we actually have step up, step down, and another type called auto transformers. We have 3 different types of transformers in our X-ray machines, and these are all used to send power into different parts of the equipment at different levels, at different power levels, so different voltages and different amperages. One part of the circuit needs low amperage, normal voltage. One part needs high voltage and low amperage. Other parts just need low voltage, low amperage. So we need to be able to adjust the power going to each part of the circuit, and these transformers allow us to change the power. So that's what's happening, on your power lines, right? In order to get the power, the electricity, the current from your power plant to your house, right? It takes a lot of push to push those electrons through those long power lines. Even though they're shaken back and forth like alternating current does, it still takes an enormous amount of oomph, push, voltage to push electricity through power lines over hundreds of miles or whatever, right? So I don't know the exact voltage in our power lines, but it's in the thousands of volts, okay? When you have your home, you access 110 or 220 volts. The power lines have to use step-down transformers to send the power from the lines to your home, okay? In our X-ray machine, we have to take the stepped-down power and then step it back up so that it's useful for making X-rays. So that's a transformer. We'll talk more about them in just a little while. Let me finish with a couple minor notes on the controls the things we want to be able to control, okay? So we use a number of devices built into the equipment to control the amount of power that we're putting through the equipment. The power law, right? Power is equal to amperage times voltage, okay? So the total amount of power you're using in your equipment, okay, is given as a number called the power number. We express it in units of watts, okay, and it's just volts times amps. So, for example, if I had a 10 amp circuit, okay, operating at 110 volts, what would my power be? 110 times 10? 1100, okay? So I would have 1100, my watts would be 1100 watts, okay? Volts times amps equals watts. So we want to be able to adjust the total power that we're using to create X-rays. We're trying to make an X-ray beam, and each part of the body needs a different amount of power, okay? So we will need to be able to change the voltage and the amperage used, okay? So in an X-ray machine, the voltage number that we mess with is not in single digits, right? We get 110 volts from the wall, but when we make settings on our equipment, we set something between 50,000 and 120-ish thousand volts. So we use a unit called kVp, kilovolt peak or potential. P can be interchanged, but kV, sometimes we just say kV, okay? Kilovolts. Kilo kilo means 1,000 of something. Okay, so if something weighs 1 kilogram, okay, then it weighs 1,000 grams. Okay, that kilo is just the unit for 1,000 kilovolts. So we have a kilovolt control. At the X-ray machine console, the kilovolt controls are settings made with a device called an auto transformer. I'll talk more about auto transformers later, but they're like a transformer that doesn't have another side. So there's no magnet and there's no other side. There's no secondary side to an auto transformer. But anyways, if you want to change the voltage, you need a transformer. Transformers adjust voltages in equipment.
And we can build them to do whatever voltage. We just
Arbitrary
have to pick
specification.
on.
Yep, you change the number of windings, from one side to the next, or where you tap into the number of windings.
Like with the power lines, when they have the step down
Yes,
facility, we see the big thing with all the wires coming in.
yes.
So is there just one transformer that's doing that step down, or do they put a series of steps?
So there's
step down?
one every so often, right?
Right.
So and like if somebody happens to run into the power pole that has your transformer running to your house and all the other houses within a couple of blocks go out, right? So they're periodically throughout the circuit where they need. So they can only send power so far. Yeah. So they have to be like every couple of blocks, something like that, at least in the power lines that feed our houses and homes. Okay, good. So your KVP adjustments, that help? That help at all? Okay, good. Your KVP adjustments, we have two. We call them major and minor. Okay? When you need to adjust just a little bit, changing from 60 to 62 kV setting, right? When you need to adjust things by a little bit, for small differences in a body part, okay? Moving from a finger to the hand, taking an x-ray of the finger to an x-ray of the hand, small differences, right? In thickness and tissue density, so minor adjustments are appropriate there. If I want to make a little adjustment, I adjust the setting called KVP minor. And if I want to make big changes, if I'm taking an x-ray of a hand, which uses a setting of about 60 kVp, 60,000 volts, then I move to a chest, which uses settings around 120,000 volts, right? I'm going to make my adjustments using the major adjuster, okay, KVP major. So when you get into my x-ray room, this is an example, it's a little bit haphazardly written all over, but this is an example of an x-ray control console, okay? It's got a timer here to time the exposures for. It's got KVP major setting and minor setting, okay? And I've got my milliamperage over here, which I'll talk about in a second. But in my x-ray room, I have a console too. It looks different than this, but it has a major setting and a minor setting, right? If you want to set, 50, 60, 70, 80, 90, 100 or more kV, you make changes of 10 at a time, the major setting is appropriate for that. But if you need to set 85 kV, right, then you have to use the minor setting as well. So this is a small idea that you just have to use two different knobs. You have a question? Okay. So you have to use two different knobs to make your KVP setting. Oh. Just let me know when I forget, because I can't see that on my screen. Looks ugly. Okay. All right. So that's KVP. KVP is what for an electric circuit, like a battery feeding a flashlight, right? What is voltage? What's voltage do?
It's just.
Oh, hang on. Joshua had something, and I think you guys had something to say. What's up, Joshua?
That gives power.
Gives power. In what way? I think you're onto something. Let me see if Michael and Lewis have something to say.
Voltage is the speed of the electrons moving.
Right. So what is the electric current? Like what makes the electric? What is the electric current made of? Electricity, which is electrons moving through a conductor, right? Michael says it's the speed of the electrons moving through the conductor. Okay. Well, Lewis, what do you got?
The push.
Good. It's the pushing what?
Electrons.
Through the
Why?
Which is a
Conductor.
conductor. So it's the pushing the electrons through the conducting wire, right? Michael says it's the speed of the electrons, Lewis says it's the push, both are right, okay? A higher voltage exerts a greater push, okay, or push or pull, doesn't matter, right? Higher voltage exerts a greater push or pull, moving the electrons faster through the circuit. Faster moving electrons means more power. So Joshua, Michael, and Lewis are all right together, right? More power from higher voltage, okay? Electrons move faster when the voltage is higher in any circuit. Now, one thing we'll learn in later, hopefully today, is that we'll need the electrons to be moving extremely fast through a open space gap in the X-ray tube so that we can use their speed energy, their kinetic energy, and harvest that to create X-rays, okay? So we need to know that voltage is the thing that pushes electrons through a circuit, and then next we need to know that amperage is the electrons moving through the circuit. How many of them are moving, right? So, thank you guys, that was good. So, at the X-ray machine console, there's a setting called MA, milliamperage, okay? Where kilo means 1,000 of something, milli means one 1,000th. So a milliamp is 1/1,000th of an amp. Recall back to here. So Ohm's law is hugely important for understanding this stuff, right? Recall back to Ohm's law, okay? Remember that we get 110 volts from the wall, okay, at some amperage, okay? We need to take that 110 volts and turn it into 100,000 volts, okay? So we need to increase the power 1,000 times, let's say, okay? Ohm's law says if you increase voltage, one of these two has to change, okay? Let's say, for the sake of this, that we fix resistance. Resistance stays fixed, is taken out of the equation, is a constant in the equation. Transformers, right? Transformers use the idea that we take, and with the transformer we raise resistance, right, to raise voltage, okay? The outcome of that is the intensity, the amperage has to decrease, okay? Voltage and amperage have this, if resistance is left alone, would have a direct relationship. This goes up, that has to go up. But because voltage is increased by raising resistance, the amperage has to decrease, okay? So in our X-ray circuits, we use thousands of volts and thousandths of an amp, okay? High voltage, low amperage. Fast moving electrons, but we don't need that many of them. Current is the number, right? Number of electrons. So fast moving electrons, we don't need that many. So high voltage, low amperage. For that reason, we have a setting, not an amperage setting, but a milliamperage setting, okay? Over on our X-ray control consoles, we will access between 50 and 300 milliamps, 50 to 300 thousandths of an amp. So not even a full amp of current. So the purpose of the X-ray circuit is to provide, this should say low, to provide low amperage current to the X-ray tube filament, heating it to extremely high temperatures, high friction, and we'll learn what happens to this high friction in a little while. It's like a light bulb, okay? Light bulbs send electric current through a filament, right? Light comes out of the bulb, okay? In this case, we're going to use electric current to cram electrons into a small filament, and we'll find that we can cause them to jump off of the filament towards this spinning disc. And we'll see what happens with that when we do that in a little while, to make x-rays. But we have a setting called the milliamperage setting to control how many electrons move through a circuit, ultimately controlling how many x-rays we make. Okay, so on an x-ray machine, kVp and amperage are your two main settings. One controls how fast the electrons move through the circuit, the other controls how many move through the circuit. Okay, what this comes to mean for your x-ray beam that you make. Okay, so again, it's not just pushing a button, right? What this comes to mean for your x-ray machine is, with voltage, you can control the power of the x-ray beam, how penetrating it is to the body. And with amperage, you can control how much of an x-ray beam you make. Higher amperage equals more x-ray beam. Higher voltage equals more energy in the beam. And we'll later, in an upcoming module, we'll see how those ideas change the image qualities. Okay, we just need to start learning that they are ideas. Okay, good. So that is the end of this section. Let's go ahead and move on, and let's talk